Welcome dear students to this lecture on lateral arc pressure. This is our second lecture, and in the first lecture what we had learned, let us recap. We studied the three types of arc pressure, namely the arc pressure at rest, then active arc pressure and passive arc pressure. And we also studied the Rankine's theory of arc pressure, and we got the values of or expressions for coefficient of arc pressure at rest, then coefficient of active arc pressure, and also passive arc pressure, coefficient of passive arc pressure. And we have studied how the failure mechanism that operates in active and passive cases, how the failure circle moves from at rest condition to the active condition or the passive condition. And we have seen the inclination of failure planes in active and passive cases as per the Rankine's arc pressure theory. Now in today's lecture we will study these things: how the arc pressure varies with depth, alright, how it varies with depth, because arc pressure is a product of the arc pressure coefficient with the vertical stress at any point, total vertical stress. Therefore the variation of arc pressure will be similar to the variation of vertical stress within a soil mass. We will also take up one simple example for that, and then we will study how the arc pressure changes due to presence of some surcharge load on the surface of the backfill. Then we will study, in fact we have already got the Rankine's arc pressure coefficient for C5 soil, and we will use that to find out something called the depth of tension crack, how the tension occurs. And then we will also study the arc pressure behind a vertical wall when the backfill surface is inclined at some angle with the horizontal. That happens in most of the cases in braced walls near the hill cuts. The hill is already sloped, and near the highway we may have a braced wall, and in that case my backfill will be inclined. Okay. Then we will come to Coulomb's arc pressure theory, its assumptions, limitations, and how we can use it. We will just introduce this. We will not solve actually any problem on this. So this is our topic of discussion today. Now let us go to this let us see how the arc pressure varies with depth. Now we know that, suppose I am considering active arc pressure. In that case I know that horizontal stress at any depth z will be the vertical stress at that depth times coefficient of active arc pressure. Okay. And therefore suppose I have a vertical wall. Let me draw a small wall, vertical wall, and say I have a backfill behind it. Suppose it is a uniform backfill having the same, say, gamma, and say this height is say h. Okay. this height is say h, and my job is to find out how the earth pressure varies. If I have it's a cohesionless soil, so the value of phi is given as phi. In that case, if I measure the depth from the surface of the backfill, say Z, then at any depth Z, if I consider a soil element, then sigma Vz is how much? Gamma into Z, sorry, gamma into Z, and therefore my sigma h at that depth Z will be my gamma Z times Ka, and therefore it is linearly varying with Z, right? And therefore if I draw the earth pressure diagram, Z is 0, so earth pressure will be 0 here, and it will vary as a straight line, and it will be maximum at the bottom where I have the depth as Z, h, and therefore this value will be how much? At the bottom my earth pressure will be Ka times gamma times h, right? And therefore my earth pressure diagram will be this triangle. This triangle is giving me the variation of earth pressure. Okay, this is my earth pressure diagram, obviously, and therefore it varies linearly with depth, and the area of this earth pressure diagram will give me the total earth pressure. So if my total earth pressure, if I call it say Pa, which will act in the horizontal direction, of course, so this is my P, this is my Pa, active earth pressure, total active earth pressure. So Pa will be how much? It is the area of the earth pressure diagram, so half Ka gamma h times h. This is my area of the triangle, so it is half Ka gamma h square, and it will act, the net, the total earth pressure will act at the CG of this earth pressure diagram. Therefore its height will be how much? Its height will be h by 3, because CG of triangle is at 1/3 height, right? Therefore it will be, say, this will be h by 3. Alright, my diagram is not good, the space was limited. Let me show it here. I think that will be better. So this height is h by 3. Okay, so this is how earth pressure varies with depth. If it is an active earth pressure, I will use Ka. If it is passive earth pressure, I will use Kp, and if it is earth pressure at rest, I will use K0. So appropriate earth pressure coefficient I'll have to use in the to get the necessary earth pressure. Okay, in case of a vertically standing wall with a horizontal backfill. All right. Now if there are different layers of soil, then appropriate gamma I will have to use. All right. Say in the second case, suppose I have two different layers. All right, and say this is another layer, say so what will happen, say this portion has a gamma of gamma 1 and phi 1, and this portion has gamma 2 and phi 2. Okay, in that case my active earth pressure will be, let me draw it here. So this portion will be how much? This portion will be, let me take a dotted line for this. So this portion will be Ka1, because it will depend on the phi 1 value. So Ka1 gamma 1 into, say this is my H1, this is my H1, and this is my, say, H2. Okay, so Ka1 into gamma 1 into H1 will be my earth pressure here. And then at this point dispatch pressure will remain same throughout this, because it is already acting due to the first layer of soil, right? So I will have, let me draw another dotted line. So this will remain constant, I'm sorry, this will remain constant up to the bottom, and then with another slope depending on the value of Ka2 I'll have another linear variation. Okay, all right. So now this value will remain same as Ka1 gamma 1 into H1, and this value will be how much? Ka2, I'm sorry, Ka2 into gamma 2 into H2, right? So this will be my variation of earth pressure. And if there is also groundwater table, say I have, say, groundwater table here, in that case I'll have to use the appropriate saturated unit weight if I want the total earth pressure. If I want the effective earth pressure, I will have to use the submerged unit weight, and in addition to that there will be my water pressure. All right, in that case I will have another part due to water pressure, which will be 0 here, and which will be equal to, now this much will be how much? Gamma W into H2. So this will also be acting on in case of submergence up to this level. and in that case here I will use gamma 2 submerged in place of gamma. So that's how we can find out the variation of earth pressure along the height of the retaining wall. Now in a similar manner, if I have a surcharge, say if I have surcharge, then say my backfill is now carrying a surcharge of Q kilopascal. Okay, say this is in, let me use some other letter, kilopascal. In that case, due to this Q, there will be at the very beginning there will be some earth pressure, right? It will not start from 0 like the earlier case, but it will start with a value of Ka at z equal to 0. I'll have Ka times Q, because that much vertical pressure is already there. If I am interested in active earth pressure, I will use Ka. Here the problem is for earth pressure at rest, so they are using K naught. Okay, and that will remain constant, and then due to this portion I will have Ka1, say, oh, this gamma is same in this case, so Ka into gamma into H1 will be added to this value. So this total will be Ka times Q plus gamma into H1, right? And anywhere below this line, that pressure will remain again constant, because that much vertical pressure is always there, and then that much horizontal pressure is always there at that level, that will remain constant, and then the usual triangular variation or linear variation I will have to consider. So this portion will be K times gamma submerged into H2 here. This much will be this value, and in addition to that the water pressure will be gamma W into H2 at this bottom, and water pressure will not be having any value, that will be 0 above this line. So this will be my earth pressure diagram in this case. Alright, so if I know the numerical values of Q or gamma and phi and C, etc., then I will be able to find out the numerical value of Ka or K naught or Kp, and accordingly I'll be able to find out the actual values of the earth pressure. Okay. Now let us take up a simple example. No, okay, example we will take later on. Okay, so this is how earth pressure depends, or the earth pressure diagram changes due to presence of surcharge. Okay, so that's what is effect of surcharge. So what we can write is this remains constant throughout the depth. For example, if I can draw it here, say this line, let me use a dotted line, this pressure will remain constant throughout the depth. Similarly, due to this much, this is remaining constant throughout the depth at the bottom layer, and so on. Okay, so this is important. This is important. This fact is important. This thing remains constant throughout the depth. This is important. Next is earth pressure for C5 soil. We remember that if I consider the active earth pressure, what was the value of active earth pressure coefficient for C5 soil? It was the relationship between, we have got we have got sigma 3 as sigma 1 into Ka minus twice C root over Ka. This we got from the failure circle in case of Rankine's active case, and therefore at any depth z my horizontal stress sigma h at z will be how much? Sigma v at z into Ka. You remember what is Ka? Minus twice C into root over Ka. Now let me put the values. Sigma h at depth z will be sigma vz is gamma into z in times Ka minus twice C into K root over Ka. It means what? It means whatever was the earth pressure in case of a non-cohesive soil, you see this thing, this portion, this equation, from here I need to subtract this value twice C root over Ka. Therefore what the earth pressure will look like, say let me draw it here. Say this is my retaining wall and this is my C5 soil, horizontal C5 soil. And therefore you see this Ka is constant, C is constant, so it is constant throughout the depth. Okay, therefore if I consider at a depth z any point, say this is my z, I'm sorry, this is my z, therefore my earth pressure coefficient, my earth pressure, one part will be this triangular part. Okay, and in addition to that I have to superpose this negative portion, I'm sorry, this negative portion. Okay, so if this is positive, I also have a negative portion which is rectangular. Okay, I need to superpose, and the net area will give me the earth pressure. Okay, so net area is this much. I'm sorry, net area is this portion. So this will be in this direction because it is positive, and this will be in the opposite direction. So it will be something like tension, as if the backfill is pulling the retaining wall. Okay, so if I draw for the whole height of the backfill, then I will have a larger, more legible picture. So this is my triangular part due to this term, and the cohesive term will be just negative value here. Its width will depend on the numerical value of C and numerical value of Ka, root over Ka. Suppose this is the width in scale. Actually this should start from here. This should start exactly from this point. Say this is my negative part. Okay, so this is my negative portion, there is my positive portion. So net is negative here and positive here. So this will be my earth pressure diagram in case of a C5 soil for a horizontal backfill behind a vertical retaining wall, as per Rankine's theory. Now this portion of the soil, since it is subjected to negative stress, therefore there will be tension developed, and therefore there will be some tension cracks that may develop. Tension crack. Okay, and if tension crack develops, then later on water may percolate through those cracks, and this whole portion may become saturated, and that will give rise to additional water pressure on the retaining wall. And that's why it is important to take into account this depth of tension crack. Up to what depth there will be additional water pressure if there is rainfall also. Actually there is had it been totally dry soil, this portion of the wall will be actually sucked, not pushed away, rather pushed in by the soil, this portion of the retaining wall. But if there is water, there will be additional water pressure, and in some soils upon wetting the cohesion may get lost totally. In that case there will be additional pressure on the retaining wall, because this portion will become zero in that case. Alright, this term will become zero. Now we can very easily find out the depth of tension crack, say ZC, say this length is say ZC, this height is say ZC. Say this is my ZC. Now at ZC my total pressure is 0, so I will just equate this equation to 0, and therefore what I will get, so for depth of tension crack, depth of tension crack I'll equate this portion, this sigma hz I will equate to 0, so I will have 0 equal to gamma into zc into Ka minus twice c root over Ka if it is active earth pressure, and therefore I can solve it for Zc. So if I take it towards the this term towards the left hand side, then I'll get Zc as twice c by gamma, twice c by gamma into root over Ka divided by Ka, so 1 upon root over Ka. Alright, twice c by gamma, this term divided by Ka, so 1 upon root over twice Ka. So this gives me the depth of tension crack in a cohesive background, cohesive backfill. Okay, this is important. This equation is another important equation. So please remember this. Next is, if I have an inclined backfill, what happens is we can use the principle of conjugate stress. Conjugate stress, you remember that, see, this is my vertical wall and this is my backfill inclined at an angle alpha to the horizontal. In that case, what happens, this surface is my free from shear stress, so shear stress is 0. Okay, and Rankine theory assumes that this is frictionless because it has to be principal plane, so there is no shear stress here also. So in the same manner, I will have a soil element where this will also be a shear stress free plane, and these will be shear principal planes, and therefore my earth pressure now will be inclined at this angle, which is again alpha. Okay, and from the principle of conjugate stress, this equation can be derived. The effect of the coefficient of active earth pressure for inclined backfill is this: cos alpha times cos alpha minus root over cos square alpha minus cos square phi if it is cohesionless soil, divided by cos alpha plus root over cos square alpha minus cos square phi. So this is my Ka, and just inverse of that, not inverse of that, for Kp, what will happen is this numerator will go up, denominator will go up, and numerator will go down, come down, in case of passive case where the soil is cohesionless. If I need to use cohesive soil, then the expression becomes more complicated. I am not covering that, okay, but it can be obtained. And the resultant earth pressure, again, it will be the equal to the total area of this earth pressure diagram. Okay, earth pressure diagram passing through this point, and it will be inclined at an angle alpha, the total earth pressure. So we can find out the area of this triangle pretty easily to get what is PA, and because it is triangular, we again assume that it is at its point of application is at a height of h by 3 from the bottom of the retaining wall. So that's how inclined backfill behind a vertical wall can be handled. Okay, you can remember this equation, not difficult: cos alpha times cos alpha minus root over cos square alpha minus cos square phi and cos alpha plus root over cos square alpha minus cos square phi. And in case of passive case, this denominator will go up, numerator will come down. That is the only difference. This term will not become inverse. In horizontal backfill, Kp and Ka are just inverse. One is inverse of the other, but in inclined backfill it is not exactly so. The whole thing will not come down. This cos alpha term will not come down. Please remember that. Now let us take up this example. Let us find out what is the active earth pressure behind this wall. So find active earth pressure distribution then resultant force that means resultant active earth pressure and its point of application. So this is our problem, point of application. Now let us find out the solution. It's pretty easy because it's a vertical wall with a horizontal backfill. My gamma values are already given. It is the same soil because phi is same. Only difference is that due to saturation there is water table involved, so due to saturation gamma saturated value is given here. So let us find out the let us first draw the variation. Okay, let us first draw the variation of earth pressure diagram. Variation of earth pressure. Say this is my retaining wall. Okay, and this is exactly at the midpoint, so somewhere here I have the groundwater table here, and gamma is given 16, phi is given 30 degree, and gamma saturated is given as 19.3 kilonewton per meter cube, and what is given, phi is same, phi is 30 degree, and cohesion is 0 of course. So how will the variation occur? Let me draw it here first, and there is my vertical line. So here up to here it will be just rectangular, so this line let me extend. Let me extend this line from here for ease of understanding, and then in this portion I will have to use gamma submerged. Okay, so therefore there will be a change of slope. I do not know in which direction the slope will move, but let me assume that since gamma submerged will be less than gamma, therefore it will be the rate of change will decrease. The slope will decrease, right? So it will be somewhat like this, and in addition to that I'll have water pressure. water pressure. Okay, so let me number these different regions. Say this is area number 1. Then I can draw one rectangle here because that is acting as a searchers. So this portion will remain constant. Okay, so say this is my area number 2. I'm sorry, I should change the line type. Then this is area number 3 and this is area number 4. Okay, and these heights are given to us. This is 2.5 meter and this is another 2.5 meter. So 2.5, 2.5. Okay, now what is this portion? This portion is, say, let me write earth pressure at Z equal to 2.5 meter is how much? Let me first find out what is Ka. Okay, let me add a little space. So Ka is 1 minus sine phi. 1 minus sine phi is sine 30, which is half. 1 minus sine phi by 1 plus sine phi. And this is 1 minus half. And this is 1 plus half. 1 plus half. So this is 1 upon 3, right? This is 0.5 by 1.5, so 1 upon 3. 1 upon 3. And therefore EP at Z equal to 2.5 will be gamma is 16 times Z is 2.5 into Ka 1/3, and this is how much? This will be this will be equal to 13.33. What will be the unit? Unit will be gamma times Z, because K is unitless, so it will be kilopascal, kilonewton per meter square, but it is a pressure, right? So kilonewton per meter square, this is the intensity, and it is actually per unit length of wall in the perpendicular direction. Okay, next, so this portion, this length is this is my 13.33, and this will remain constant. Now how much is this? So now let us find out earth pressure intensity at z equal to 5 meter from the top. Okay, so next additional EP at z equal to 5 meter will be how much? Now gamma submerged I will have to use, so gamma submerged is, okay, let me write down Ka times gamma submerged times 5 minus 2.5. okay, so this will be my value. So Ke is 1/3 into gamma submerged is 19.3 minus 10 into 2.5, and this will be equal to, so this will be equal to 7.75. So let me write it down here. This much is 7.75. And how much is this? This is just gamma W times the height, that means 2.5. The water pressure, so next let me write it here. Then water pressure at z equal to 5 meter will be gamma W times 5 minus 2.5 is my U, okay, and this is equal to 9.3, sorry, I'm very sorry, this is gamma W, this is 10 into 2.5, so it is 25 kilopascal. So all are kilopascal. Now we are asked to find out the resultant earth pressure, therefore I will have to find out the area of these different portions numbered 1, 2, 3, 4. Okay, so for that let us find out the areas. So net earth pressure, so total earth pressure EP will be equal to area 1 plus area 2 plus area 3 plus area 4, and this will be equal to how much? First will be half times 2.5 times 13.33. Correct? Let us verify the pressure diagram. Yes, this is 13.33. Then area 2 is 13.33 into 2.5 plus 13.33 into 2.5 plus area 3 is how much? Half of 1 what was the base? It was 7.75. 7.75 into height was 2.5 again, plus the area due to water pressure is half into 25 into 2.5. okay, so these many kilonewtons, and this will be equal to, so this comes out to be 90.925. 90.925, and this unit will be in kilonewton, because kilonewton per meter square into area, actually it is kilonewton per meter length of wall. Okay, and what is the point of application? Point of application, I can take the static moment of this area about the base, point of application will be what? Say h dash, h bar will be equal to sum of ai hi by sum of ai, right? This I can denote as PA. Okay, so AIHI is how much? You can easily do that. So I should write down these values separately. Let me find them separately. Okay, so I calculate the individual values of these areas, and they are here, shown here. So now I can take the moment of all these areas. So first term will be 16.66 into what will be the lever arm? Lever arm will be, you see, it will be this 2.5 from the bottom plus 1/3 of 2.5. okay, so it will be 4/3 of 2.5. So 4/3 of 2.5. One third plus 1 is 4/3 into 2.5. Plus 33.325 into, this is a rectangular area, so it will be at the mid height, so 2.5 by 2, so 1 point, let me write it down for your benefit, half of let me write 2.5 by 2, 2.5 by 2, then plus third value 9.688 into it is 1/3 of 2.5, so 2.5 by 3, then the third term, a fourth term, plus fourth term is 31.25 into 2.5 by 3 and this whole thing divided by total area. Total area is P naught PA, which we already have the value 90.925, and this will give me a value of, so this height of point of application from the base of the area becomes this static moment of this area is 131.304, and the total area we have already calculated in terms of the total earth pressure, which is 90.925, and therefore the height of application is at a height of 1.444. so what we can show here is my total area, total force, so it is somewhere here 1.444. so this is my, say, let me this is my total force, and this we already got as 90.925 925 kilonewton per meter, and this height is 1.444. So this completes our problem. Okay, so you can write that the earth pressure distribution is shown in, say, figure, say, 2. Let me number it as figure 2. I should write it here, but now I'm writing it here, figure 2, and this is my figure 1. Okay, so this completes our problem. This is one answer, this is one answer, and this is other answer. Okay, so we'll move to the next topic now. Okay, next we are going to discuss the Coulomb's earth pressure theory. This was another earth pressure theory, one of the oldest geotechnical theory developed by Coulomb, when he was acting as a military engineer in the islands of Caribbean. I told you this story in the last class, I suppose. So Coulomb's earth pressure theory has the biggest advantage as it considers the friction between wall and the backfill. So in Rankine's earth pressure theory, what we had assumed this wall face to be vertical, and the soil wall interface we assume to be a principal plane, and therefore there cannot be any shear stress or any frictional stress between soil and wall, which is not very realistic. Okay, although Rankine's earth pressure gives sufficiently good results for practical application, but theoretically it is not true that the soil wall and the backfill, retaining wall and the backfill, has zero friction. Now the Coulomb's theory, the advantage is that it considers the friction. So considers wall backfill friction. Secondly, the soil is again assumed as cohesionless and homogeneous and isotropic. Although Coulomb's theory can be extended to C5 soil, but in the original assumptions he assumed soil is homogeneous isotropic and cohesionless. Okay, that is another assumption. And the third important assumption, which is more realistic than Rankine's assumption, is that back of the wall is inclined. Back of the wall is inclined. With vertical. Okay, it can be used for vertical back wall also, but it is, in general, it is inclined. And this was important because those days mostly masonry walls, stone masonry walls were constructed, and for the strength purposes and bearing capacity purposes, the wall had to be thicker at the bottom and thinner at the top, and therefore it invariably had some inclination. The back of the wall invariably had some inclination. Okay. Then third, next assumption is that the position of net earth pressure is known. That means total earth pressure, force, position and the line of action, and its line of action is known. That means direction is known. Okay, so this is another assumption. And it also assumes that the soil is a rigid plastic material. So when the soil fails due to active or passive condition, a rigid block of the soil is there which is applying forces on the wall. Okay, so soil fails as a rigid block. That is one more assumption. The sliding wedge of soil is assumed to be rigid. To be rigid. And the next assumption is, let me add little space. The next assumption is that failure surface is planar. It's a plane and passes through the heel of the wall. Okay, well, it is obvious that if backfill is in this direction, then this will be my heel of the wall and this will be my toe of the wall. Okay, so that's why Coulomb assumed that the failure surface of the wedge passes through this heel and it's a planar surface. Okay, so these are my assumptions. Now what we do is, in Coulomb's method, let me slightly increase the size so that you can see the figure more clearly. You see, what we do is, we assume that there is friction between soil and wall, and when it is an active case, what will happen? In active case, my wall will move away from the soil, therefore the wedge will move downward, and hence, as we discussed in the earlier class, the shear resistance on the failure plane will act towards up. And in addition to that, on the failure plane there is a normal force acting due to the remaining part of the soil. Okay, and that acts just in a perpendicular direction on a perpendicular, along a perpendicular on the failure plane. Okay, and therefore in active case, since my shear resistance is working upward, therefore the resultant of this normal force and an upward force, okay, that will give me the resultant of the total force on the failure surface at an angle phi, because this is soil to soil friction is happening, so it will be inclined at an angle phi with the normal to the failure plane, and that angle will be towards the down. That means the resultant will be below the normal direction. Okay, because you see this force, this resultant will be equal to this force plus this force. If you consider vector addition, then this resultant will be resultant of this force plus this force will give me this resultant, and since this is upward, this must be below the normal at an angle phi. In a similar manner, since there is wall friction between wall and the soil, and say that angle of friction is delta or delta dashed here in this figure, in that case this resultant active earth pressure will be working below, will be acting below this normal to the inclined wall surface at an angle delta. This delta is the angle of friction between soil and wall. So the soil active force and the wall friction, there at an angle delta, and therefore it acts at an, that friction angle is delta, therefore it acts at an angle of delta. Again it is below the, because this wedge is moving downward, so frictional force must be moving upward, and therefore this resultant active force will be below this normal to the back of the wall. Okay, so by knowing all these, and by knowing that my failure surface passes through the hill at, it is inclined at some angle theta 1 say with the horizontal, and the angle of inclination of the wall back is say beta, then from the geometry it can be shown that this resultant force, this resultant is resultant of what? The normal load, the normal force, and the frictional force or soil friction, soil to soil friction or shear force on the failure plane. So that force and the direction of the wall, direction of the weight, I am sorry, vertical, that angle will be theta minus phi. If this is theta 1 and the angle of friction, internal friction of the soil is say phi, okay, it is already written there phi, that's, so this angle will be theta minus phi, and similarly the other angle will be beta minus delta, beta minus delta. So this angle is theta minus phi, it is the angles acting towards right of the failure plane, and this angle is the angles related to the back of the wall, that is beta and delta. That way you can remember. Okay, and now what I can do, I can, from the density of the failure wedge, I know what is the W, what is the weight of the wedge, and I know the direction of this R, the resultant force, because it is at an angle phi to the normal to the failure plane. So I know the direction, I know the direction of this force also, so I can draw a force triangle and find out the equilibrium condition, and from that equilibrium force triangle I can find out in scale what is the total active earth pressure. So this is pretty simple, just your basic engineering mechanics tool we are using here. The force polygon we are drawing, since I know the direction of the three forces and I know the magnitude of one of the forces, so it is possible for me to find out the magnitude of the other two forces simply by drawing this force triangle, and from here I can find out the active earth pressure. And now since I do not know the actual failure plane, so what we do, we make a trial with different angles of failure planes, and accordingly I will have different force triangles, because this theta will be changing every time. So accordingly I will have different force triangles, and accordingly I will have different values of PA. Alright, and that PA I can plot with I can plot this active earth pressure for different failure planes, and the maximum that I get out of all these wedges, the maximum active earth pressure that is acting on the wall, I can get from this kind of graph. Okay, so it's a graphical and trial and error method. The biggest advantage is that we can take into account the inclination of the back wall, the effect of friction, wall soil friction, and of course the effect of shearing resistance of the soil, and my backfill can be either inclined or it can be horizontal. Accordingly, what will change? It will change only the weight in the force triangle. Okay, and therefore solution can be easily obtained both for inclined backfill and horizontal backfill. Okay, and that is how we can find out the active earth pressure in using Coulomb's theory. Okay, now there are some limitations, of course, of any theory. So one limitation here is we have seen that what we assumed is that the failure surface is a plane passing through the heel of the wall. I'm sorry. Actual failure surface, due to the effect of the friction between wall and soil, what happens is that it becomes slightly curved, both in active and passive cases. In active case, this curvature is not much, because this angle is 45 plus 5 by 2 with horizontal, you know, and therefore I quickly get a straight line, and therefore the error involved in using Coulomb's theory for active earth pressure calculation is less. The actual earth pressure will depend on this true wedge, failure wedge, and this true wedge is curvilinear towards the bottom of the wall, that means near the heel, and since the amount of curvature is less in case of active earth pressure, therefore Coulomb's theory gave good results in case of active earth pressure. But in case of passive earth pressure, what happens? The actual failure surface is much more curved near the heel of the wall, and that is disregarded in Coulomb's theory. I can show you the passive case here. We again assume the similar wedge, but now what is happening? Since the direction of wall movement is different, the wedge is being pushed upward, therefore the shear resistance is downward, and that's why my resultant force will be at an angle phi above the normal to the failure plane in this case, and similarly the passive earth pressure will be at an angle delta above the normal to the inclined wall face, and therefore my angles of this R and PP will be different. So these angles will be, earlier it was theta minus phi, now it is theta plus phi. Similarly, earlier it was beta minus delta, now it will be beta plus delta, because it has gone in the opposite direction. Okay, so remembering that, we can find out the Coulomb passive earth pressure in a similar manner, and in this case we find the minimum force which causes the failure. Okay, so corresponding to one of the wedges, I will get the minimum force, and that will be my passive earth pressure. Okay, now since I am assuming planar failure surface in passive earth pressure condition, and in the true failure surface for passive condition, when I include wall and backfill friction is much more different from the planar case, because this curvature is huge. It covers a large, up to a large distance from the heel of the wall. Okay, and therefore the error involved in using Coulomb's earth pressure, passive earth pressure, is higher. Okay, so this error is in the not in the conservative side. Okay, so it may lead to some unconservative design if we go for passive earth pressure analysis using Coulomb's theory. Okay, so that is the main limitation of Coulomb's earth pressure theory. So use of planar failure surface is the main limitation. Surface in active case, error is small, but in passive case we have large error and leads to unconservative design. Okay, so I think with this we can stop our earth pressure theories. I hope all of you understood the basic concepts, and I hope you can practice a few problems from any book if you have book, or at least you practice this problem or problem with dry backfill or fully submerged backfill. This type of problems you please practice yourself, and with this we complete this topic of earth pressure. Thank you very much.